All right, so next up in our notes, we have matter. And matter is anything with a mass that occupies space. So the key word there being anything. All those things that you normally think about, like a pencil, a book, the chair you're sitting in, you yourself, are made of matter. Right? Otherwise, a vacuum is the opposite of matter. That means you have nothing, right? You just have empty space. It's a complete absence of matter. The closest thing that we have to a true vacuum would be outer space. Now, technically, there are still particles of matter within that space, right? It's not truly empty, it's just very, very spread out. But it's about as close to a true vacuum as we can get. Otherwise, when we break down matter, we start talking about those states of matter. So, you're obviously familiar with solids, liquids, and gases. Excuse me, this pen's being goofy. Liquids and gases. But then there's also that fourth state, there's that plasma state. But typically, that's something that you'd only be worried about if you happen to be on the sun. Right? So, the sun is such a high energy situation that even the particles themselves, the atoms, have broken down further, right? The electrons are stripped directly from that atom in that high energy situation. But otherwise, solids, liquids, and gases, starting with the solids, we always like to define those by their volume and shape, right? So a solid is going to have a definite volume. Particles are really close together, and it's hard to change that volume because you can't compress them, you can't make them get any closer. Plus, they're attracted, so they don't want to spread out any further. But then solids also have a definite shape, right? Particles in a solid don't move freely from each other. They just vibrate around fixed positions. So you end up with that definite volume, that definite shape that define that solid. Right? Liquids, on the other hand, still have a definite volume, but they no longer have a definite shape. Particles are very close together again, just like before. That's where that definite volume comes from. But those particles are free to move around each other, and as long as they stay within the volume, you can take whatever shape you want as a liquid. Right? The liquid tends to take the shape of its container. Finally, you have gases. They don't have a definite volume, nor do they have a definite shape. Right? Gas particles are spread out from each other, not close together. Right? You can easily compress a gas and it can expand to take that shape of its container. Plasma, that last state, remember, not really a big issue on this planet. It's just a really high energy situation. Now, there are a few instances, like say a lightning strike, that can create plasma for short periods of time on our planet, but otherwise we don't really worry about it all that much. Not unless you're talking about reactions and things that are happening on the sun. So those are our states. Changes in matter, right? You can have physical changes and you can have chemical changes. Remember, a physical change is just altering the state. So whether you're talking about melting, boiling, freezing, condensing, even sublimating, right? Or deposition, where a gas becomes a solid directly, right? All those different state changes, as long as the stuff stays the same, right? It's a physical change. So when you boil water, it's still going to be water. It's just going to be in that gaseous state, right? That's an example of a physical change. Whereas chemical changes change the stuff, right? So you're going to have reactants and products that are actually different from each other, right? You're recombining those atoms in new ways to make new molecules, right? That's a chemical change or a reaction, right? Both types of changes include changes in energy. I do abbreviate a lot of times, so I would write change in energy like this with that delta symbol followed by a capital E. One thing there to note, chemical changes often have a much higher energy change than a physical change. right? They involve more energy than a physical change. Otherwise, again, breaking down matter more, matter can subsist of two things. Either it can be a mixture where you have more than one thing combined, or you can have a pure substance. So I could have pure water, or I could have a mixture with water, or maybe I got Kool-Aid and I got sugar and food coloring, all sorts of stuff mixed in there, right? Mixtures and pure substances can be separated, right? Mixtures can be separated into their pure substances by using a physical change. Pure substances can be broken down further as well. There we'd be talking about compounds. Again, water is a pure substance, but it's also a compound because it's made of more than one element. Right? You got hydrogen and oxygen in that substance. But pure substances can also be elemental in nature. Right? It could be one element and only one element, like 24 karat gold. Right? Again, compounds can actually be broken down to get those elements, and you would have to use a chemical change to make that happen. So again, all this stuff kind of ties together, right? Matter can be either pure substances or mixtures of those substances. You can separate those mixtures using physical changes, right? Pure substances, right, could either be compounds where you have more than one element combined, or it could just be a pure element. And you can go back and forth there using a chemical change. Finally, those elements that we talk about are represented by chemical symbols found on the periodic table. Right? I would just expect you to know a lot of the basics, right? You know that capital H is for hydrogen, O is for oxygen, N is for nitrogen, C is for carbon, right? Those are just 4 of the big 6 that I would really expect you to know in a biochemistry. We talked about those in biology as well. Those macromolecules that make up living things are mainly made of carbon, right? Carbon and hydrogen to make those hydrocarbons that we'll talk about later in organic chemistry. But then you sprinkle in some of those other elements that give them their unique properties, right? So you have oxygen, nitrogen, and we're missing here phosphorus and sulfur, right? Between those 6 elements make up the majority of the molecules that are important in reactions in your body. So they're going to be really big for biochemistry. Otherwise, there are a lot of elements that are found in trace amounts in your body. Say like the iron that you find in your hemoglobin to reversibly bind oxygen and take it to your cells, right? Or maybe even electrolytes like calcium, potassium, sodium, or even chloride ions that you might find in your body, right? So there's lots of things that are found in trace amounts, right? But the majority of the elements that make up the things that matter, the things that we're going to talk about reacting, are going to be the carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Otherwise, I think that's it for this section because we already covered density actually. So we should be good to go here.